So now that we've taken a look at ionic bonding and ionic compounds where electrons are transferred from the metal that loses electrons to the non-metals that gain electrons, we're going to take a look at the second type of bonding or the second type of glue that we're going to see that sticks atoms together. This type of bonding is known as covalent bonding. And there's a big difference that we'll see between covalent bonding and ionic bonding, and that is the type or the types of atoms involved. Okay, so in covalent bonding, we're going to see non-metals only. Okay, so that means if you are given a formula for a compound and you see a metal in there, right away you can think ionic. If you see only non-metals, chances are it's going to be covalent bonding and a covalent compound. So that's one big difference. The second difference is actually what happens to the electrons. So in ionic bonding, we saw that metals lose electrons and non-metals gain electrons. So there's a transfer of electrons. In covalent bonding, there isn't a transfer. There's actually the sharing of electrons. And again, this is going to be between non-metal atoms. Okay, and then we're going to compare this versus the transfer of electrons between metals to non-metals. And we see that in ionic bonding, right? Just to give you a frame of reference for where we're coming from. So let's take a look at how this happens. And the thing we want to keep in mind is the same thing we introduced at the beginning of this section, which is stability, right? So why would these want to share electrons? Well, to become more stable, this is just another way by which they can achieve that stability. And again, our guiding principle here is going to be the octet rule, okay, which means that in most cases, the atoms will want to have a total of 8 electrons around them. There are going to be some exceptions, and we'll take a look at a very important exception at the very beginning here. And let's look at the simplest case of a covalent compound, covalent molecule, and that is hydrogen. So hydrogen actually exists under normal conditions, not as H, but as H2. So it's referred to as diatomic, meaning it's made up of 2 atoms. And how does this actually happen? Why does it exist in this state versus just regular monoatomic form? Well, it has to do with stability. So if I have a hydrogen atom like this, okay, based on what we talked about previously, we can represent its valence electron. It's in group 1. So it's got 1 valence electron like that. If I have another hydrogen atom close by, it's got its 1 valence electron like that. So the nearest noble gas to hydrogen, the nearest thing that's the most stable, closest to it, is actually helium, He, and helium has 2 valence electrons. So this is an exception to the octet rule, right? So the nearest noble gas, which is what all the atoms want to be like in terms of the valence electrons, the nearest noble gas to hydrogen is helium. Helium has 2 electrons in that first shell, and that makes it super stable because that first shell can only hold 2 electrons, right? So that first shell is full for helium. So in order for the hydrogen to be like helium, well, this one here on the left needs 1 more electron. The one on the right needs 1 more electron as well. Obviously, if one loses one and the other one gains one, one's going to be happy, the other one's going to be very unhappy. So the way that they solve that problem between them is they actually share these 2 electrons. And we can represent that just by outlining it like so. So we have these 2 electrons now that are shared between one H and the other H. So now you can think of those electrons as belonging to the hydrogen on the left, but by the same time, because they're being shared, they also belong to the hydrogen on the right side. right? So now both of these hydrogen atoms are happy, and this is why hydrogen exists in the form of H2. It's a diatomic molecule. The way that we represent that arrangement is we say H, and then there's a single line between the H and the other H. That here represents those shared electrons. So two electrons that are shared, and we refer to that as a single covalent bond. Okay, that's the terminology that we're going to use. And in a single covalent bond, two electrons are shared, right? And it's just a single line between one atom and the other one. All right, so by doing this, both hydrogens are actually more stable than if they were existing individually, right? And that's the reason why H2, why hydrogen exists as H2 rather than H. If you take a look at maybe a couple other ones, we can maybe make some other conclusions. So let's take a look at, let's do oxygen. Okay, so oxygen, you probably know, exists under normal conditions as O2, which is also diatomic. Okay, not O. So when you breathe in air, the air has oxygen in it. It exists as O2. So why does it exist as O2 rather than O? Well, we can do something similar. So there's my oxygen. It's in group 6. So it's got 1, 2, 3, 4, 5, 6 valence electrons. Okay, it wants to have 8 now because it's going to follow the octet rule. So it wants 2 more. It's a lot easier for it to get 2 more rather than to lose 6. Well, if I have another oxygen close by, it also has 6. 1, 2, 3, 4, 5, 6 valence electrons. Guess what they can do? Very similar to the hydrogen, they can start sharing electrons between them now. And if they share one pair of electrons, okay, then the O on the left has 2, 4, 5, 6, 7. But still needs one more. Guess what? It can share another pair of electrons between them as well. So now what we have here is this O on the left has 2, 4, 5, 6, 7, 8. So it's happy. The O on the right has 2, 4, 5, 6, 7, 8. It's also happy. So by sharing now 2 pairs of electrons, we make both of these oxygens a lot happier than if they were individually. So the way that we would express this, just like with the hydrogen case, we have an O and another O. Now the bond between them, the glue that's connecting one O to the other O, is a line which represents 2 electrons, but then we have another 2 electrons, so we need to draw another line between them. So this, it's not a single line, there's 2 lines. That's called a double bond. Okay, both of them are referred to collectively as a double bond. And in a double bond, guess what? 4 electrons are shared between the O's. And we still have, remember, we still have the 2 sets of electrons that remain. So 1 pair and another pair. And then on the other oxygen, okay, we still have those 2 that remain as well. All right, and that accounts for the 8 electrons around each of these oxygens. Now, the way that we sort of differentiate between these electrons here, these are the bonding electrons, right? Those are actually stick the oxygens together. The ones that are not involved in bonding, that are usually off by themselves, we'll highlight these in orange. Okay, these are non-bonding electrons, they're not involved in bonding. And sometimes we refer to these as lone pairs of electrons. Because they're by themselves and they occur in pairs or groups of 2, right? So we have 2 sets of lone pairs on each of these oxygens. All right, so we have single bond between the H and the H, just a line, that's a single covalent bond. Between the O and the other O, we have a double bond, so 2 lines, 4 electrons total shared. And then we have these non-bonding electrons that remain. Let's take a look at another example. if we have something like, let's say nitrogen, again, nitrogen exists as, under normal condition, exists as N2, not N. So just N on its own. So it's also diatomic. Okay, and we can rationalize now why that's the case. If I have a nitrogen, nitrogen is in group 5, so it's got 1, 2, 3, 4, 5 valence electrons. I have another nitrogen over here, also has 1, 2, 3, 4, 5. Okay, each of these wants 3 more. Guess what they can do to help each other out? They can start sharing one pair of electrons, another pair of electrons, and then a third pair of electrons between them. So now the N on the left is going to have these 2, 3, 4, 5, 6, 7, 8. That N's happy. The N on the right has 2, 3, 4, 5, 6, 7, 8. So it is also happy. So the way that we would represent that would be an N connected to the other N. And now I have 3 pairs of electrons. So 1 pair, 2 pairs, 3 pairs of electrons between them. And I still have my non-bonding or lone pairs left over to account for the octet on the nitrogens. So now what we can say is the nitrogens are connected by this, and that 3 lines would be called, guess where we're going? That's called a triple bond. And in a triple bond, in total, we have 6 electrons that are shared. Okay, remember, we still have our lone pairs or non-bonding pairs that are left over. All right, and that's why nitrogen exists as N2. So in all 3 of these cases, these are covalent molecules. So covalent molecules, those are the units or the entities or particles, whatever you want to generalize them as being, that result when you have covalent bonding, right? So covalent molecules are formed from covalent bonding. So we refer to the N2 here, for example, as a diatomic molecule. Okay, and it exists because of the covalent bonds, the triple bond in this case between N and the other end. So there are several elements in the table that exist as diatomic molecules, and they undergo a similar type bonding pattern. So let's list what these are, because it's important to know that under normal conditions, these elements that exist as diatomic molecules. So the first one, we've done that one, H2, so that's hydrogen. We also have nitrogen, so N2. We have oxygen, O2. We have fluorine, F2. We have chlorine, Cl2. We have bromine, Br2. And then we have iodine, I2. Okay, so if you were to see where those are on the periodic table, there are 7 of these, by the way, that exist as or in that diatomic form. If we find where these are on the periodic table, you can see that they form a nice little pattern. So there's the nitrogen, and there's the oxygen and the fluorine. And then we also have the chlorine, the bromine, and the iodine. So if you were to outline these, where these elements are found, you can kind of trace a pattern here that kind of looks like, you don't have to imagine too much. It looks like a number 7, right? Because there's 7 of these. Well, if you count, there's 1, 2, 3, 4, 5, 6. Where's the 7th one? Well, that's hydrogen over here, right? So those are the 7. See, the H is not part of the same location, but those are the 7 that exist under normal conditions as diatomic molecules, right? So these are simple examples of covalent bonding And wherever we see, and this is the notation that we're going to use, these lines that represent two electrons that are being shared. Sometimes we will have some of these lone pairs left over. As we start looking at bigger and bigger molecules that are made up of different atoms, it's the same sort of way that we want to interpret them.